Did you know that you can use supervised classification algorithms for density estimation? In this video, I want to talk about a really cool classification-based method for density estimation that you don't usually see in machine learning courses. Suppose you are given a set of data points and you want to find the probability density function they are coming from. Let's write the data points of interest in red with the density that we write p of x. In the next step, we add an equal amount of additional points that we simulate from a second density, here denoted p0 or p0, in cyan. How does this help? We can give all data points a label that we denote y. If the data comes from p of x, that is the original data, we give it a 1. The new data that we simulate from p0 of x is given a 0. Applying Bayes' theorem, we can then compute the probability of classifying a data point x as belonging to the red class as the ratio p of x over p of x plus p0 of x. This classifier, we call it d of x, is the best classifier we can possibly get. We can use this expression, d of x, to find the density p of x in red. Remember, this is a density estimation problem that we want to solve. The only thing that is left is to rearrange this term so that we have p of x in red isolated. The first step in doing so is to multiply. From here on, it's relatively straightforward to isolate p of x. We can subtract on both sides, bringing p of x times d of x on the other side. We can add new parentheses again, and subsequently the only step that is left is dividing again by 1 minus d of x. Now we have solved this equation for p of x, and we thus have a formula to compute p of x if we given a classifier d of x. The problem with this formula in practice is that d of x is usually unknown. In practice, we need to find a classifier or train a classifier that is able to give us an estimate of d of x. This amounts to finding a classification algorithm that provides us an estimate that we write d hat of x that approximates this probability of belonging to class number 1. Particularly well suited for the task at hand is logistic regression. This is because logistic regression models the log-odds ratio with a function denoted f of x. The odds ratio, d of x, divided by 1 minus d of x, is precisely the quantity that we saw earlier in the formula. Logistic regression can come in various forms. For approximating the function f of x, we can use classical logistic regression, semi-parametric versions, kernel logistic regression, or even neural networks. As an example, I use kernel logistic regression in the following dataset. To demonstrate how this method works in practice, I've prepared 100 samples from bivariate distribution. To apply the classification approach, we need to sample a reference distribution for comparison. Here, I take 100 samples from a uniform distribution in cyan that covers the original data. We can now learn a kernel logistic regression algorithm that can distinguish those two classes, and we can use the class membership probabilities to translate this into a density estimate. In my own research, I have applied this technique for likelihood-free inference, in particular with an emphasis on time series analysis. A link to the video can be found here, and a link to the papers in the description. If you find this video helpful, feel free to let me know by pressing the like button.